All right, so in the last video, we talked about the Carnot principles, and we said really what happens is the efficiency of a Carnot heat engine or any other reversible, right, or any other reversible heat engine or any other reversible cycle. The efficiency of a Carnot heat engine or any other reversible engine cycle is only going to be dependent on the temperatures at which it's exchanging heat to operate. These temperatures now set the limit. So remember earlier in the chapter, we talked about, hey, you've got these efficiencies. And oh, by the way, if you use the first law equation for the net work out, you can massage this equation into a function of the ratio of heat transfers. Here's why that's important, because we can show that the limit for the reversible device becomes the ratio of heat transfers is equal to the ratio, this ratio of temperatures. All right, two things of note here. Note, T is in Kelvin or Rankine. I must use an absolute temperature for this ratio to work. Negative signs blow this thing up. Also, I'm not saying that QH is equal to TH. Some poor soul will do this on an exam, and you will not like the lack of partial credit you will get. I'm not saying that heat is temperature. These are two different things. Hopefully that's starting to sink in. Heat is not temperature. Heat is driven by temperature. Heat is not temperature. One is energy, one is temperature. These are different dimensions, therefore they're different quantities. However, if the process is reversible, and as in the case with the Carnot device, if the process is reversible, then the ratio of heat transfers is equal to the ratio of temperatures so long as those temperatures are in Rankine or Kelvin. And the same units, top and bottom. They both have to be Rankine or they both have to be Kelvin. Okay, so yeah, so if T is in Rankine or Kelvin, the maximum efficiency for any heat engine is set by this limit. That's what we call the subscript here of TH, the thermal efficiency, if the device is reversible, is based on this limit, 1 minus TL over TH. And I think I've already said this before. Yeah. If the calculated efficiency is less than the efficiency for Carnot or any reversible engine, right, or reversible, doesn't have to be Carnot, it just has to be reversible. So any reversible engine, if we have an efficiency that we calculate and it is less than the efficiency of that reversible device, we have an irreversible device. Perfectly normal device. This is what we expect. In fact, if we get an efficiency that is greater than the reversible limit, that means it is a perpetual motion machine. It means it doesn't exist. It's impossible. Similar, remember we said you can apply the Carnot cycle to a refrigerator because we can run this in reverse. And the reverse of a refrigerator is essentially a heat engine. So if we run this in reverse, we get a Carnot refrigerator. So COP for refrigeration also works. And a heat pump is also just a kind of a special application of a refrigerator. So the same logic applies that I can take the ratio of heat transfers and set that equal to the ratio of temperatures for a reversible cycle. Therefore, this sets the limit, right? COP for any refrigerator we might construct is going to be less than or at most equal to the COP for a refrigerator operating reversible. This sets the limit of coefficient of performance for these devices. Same thing with the heat pump. And then we've got a simple example. Not a bad place to stop this video, and we'll start the separate video for an example.